fine-tuning a billion-parameter model used to require a dedicated workstation or a complex cloud setup. Now it's accessible through a standard text editor. For years, AI developers faced a strict compromise. You either wrote your code in a professional local environment like Visual Studio Code, or you ran your models in a browser-based notebook like Google Colab to get free GPU access. This dual workflow created constant friction. You'd write a script locally, copy it to the browser, realize you missed a dependency, and by the time you were ready to test, your browser session had often timed out. That disconnect is over. Google released an official Colab extension for VS Code, creating a direct bridge between local project files and remote Colab runtimes. Instead of migrating code to the cloud, your local editor becomes a thin client. You write, debug, and manage version control on your own hard drive, while the actual code execution happens on a Google server. To understand how this works in practice, we need to examine three things: the hybrid file system architecture making this possible, the actual hardware limitations of the free tier, and the precise benchmarks of fine-tuning a 14 billion parameter model on a free GPU. If you rely on technical breakdowns of modern development environments to build your stack, make sure to subscribe. By bridging the local IDE with cloud compute, this integration allows a standard laptop to perform like a dedicated AI workstation for iterative tasks. Building this bridge requires solving a specific engineering problem: how to split the local interface from the remote execution environment without exposing your local hard drive to cloud security risks. The foundation relies entirely on Microsoft's existing Jupyter extension. This handles the rendering of the notebook cells, the syntax highlighting, and the variable inspector natively within your editor. To execute cells, the extension initiates an OAuth 2.0 flow, generating a secure token to command the remote machine. But continuous two-way synchronization of your entire local directory to the cloud would create severe latency. To solve this, Google implemented an asynchronous hybrid file system. It does not sync everything automatically. Instead, developers manually trigger uploads for specific datasets or supporting Python modules. From the VS Code Explorer panel, you simply right-click a file and select Upload to Colab. The extension then pushes that single asset directly to the remote/content/directory. Because the bulk of your files remain local, your language servers stay active, your linters check instantly, and auto-completion remains perfectly responsive. This selective synchronization is what makes the workflow viable. It provides the low-latency feel of a local desktop environment, right up until the moment you command a cloud GPU to process a massive dataset. Once connected, the reality of the hardware takes over. For free tier users, that hardware is almost always an NVIDIA Tesla T4. Looking at the hardware tiers, the T4 offers 16 GB of VRAM and an architecture optimized for mixed precision chaining. It sits at the bottom of a stack that scales up to A100s and Google's custom Trillium TPUs on the paid plans, while Pro users can rent massive arrays of memory. 16 GB on the free tier is a tight constraint. To train a modern language model here, you have to aggressively optimize your memory usage. This is where open source libraries like Unsloth become mandatory. Unsloth rewrites standard operations to drastically reduce memory consumption, making it possible to squeeze a 14 billion parameter model into that 16 GB limit. The performance difference is stark. We benchmarked the fine-tuning of a 7 billion parameter language model, running it first on local silicon and then remotely through the Colab extension. Running locally on an Apple M1 Max chip, the process grinds on for 18 hours, suffering severe thermal throttling. But rounded through the VS Code extension to a Colab T4 with Unsloth, it completes in just 3 hours. This creates a functional advantage for small-scale development. A 3-hour run lets you test, adjust, and complete multiple iterations in one workday, instead of waiting overnight to see if code failed. By pairing a professional local editor with highly optimized memory kernels, developers are converting heavily restricted multi-tenant cloud instances into highly capable AI laboratories. However, operating in this environment requires working around strict hard-coded limitations. Google aggressively reclaims its free hardware. Sessions face a 12-hour maximum, and after 90 minutes of inactivity, the virtual machine is wiped entirely. This ephemerality makes multi-day training runs a high risk. If your connection drops and you aren't writing automated checkpoints back to Google Drive, your progress is erased. For heavy workloads, developers eventually have to leave Colab. Platforms like Thunder Compute offer a direct upgrade path, providing dedicated GPUs for a fixed hourly rate without arbitrary timeouts. Alternatively, services like Lightning AI are built specifically for persistence. Their architecture maintains up to 50 gigabytes of persistent storage that survives session restarts, protecting your environment state. Let me know down in the comments, are you integrating this Colab extension into your daily workflow, or is the predictability of a pay-by-the-minute cloud provider worth the cost for your projects? The reality is clear. Colab provides a strong environment for rapid prototyping and lightweight fine-tuning, but once a model moves toward production, it demands the stability of a dedicated virtual machine. The integration of cloud computing and local editing alters the standard development cycle. It removes the need for physical hardware ownership for the earliest stages of model development. This integration arrives at the exact moment the broader AI hardware landscape is splitting into two highly specialized directions. This diagram maps the split. The first path is edge inference. Breakthroughs now allow complex models to execute directly on consumer hardware. Techniques like 1-bit quantization and Microsoft's BitNet framework allow 100 billion parameter models to run on standard CPUs, moving inference to the edge. But the second path, the computationally heavy process of training and fine-tuning those models, remains bound to cloud GPUs. By releasing this extension, Google has positioned Colab directly at the center of the split. They have turned their cloud infrastructure into a frictionless compute layer orchestrated right from your desktop. The development loop has moved past the need for local GPU clusters for initial prototyping. Success now depends on how effectively a developer can bridge their local environment to the scale of the cloud.